Hello everyone, I'm Katie. Today I'm going to be going over the probability and base nets worksheet. So let's jump right into it. We're going to start off by talking a bit about inference by elimination. So I have it open to the notes part of that. Notice that to solve for a certain query in inference by elimination, we do as the name implies. We have a query. We try to remove all variables that are not part of the query by summing everything out. So taking a look at this example, we notice that if we write out the joint distribution, we can sum it out quite easily over the variables that we do not want, and we will get a probability that we do want. So after we do that, we can bring the summation inside to where it matters, and from then on we can sum up the rest in order for us to get to our query. So that was pretty high level. One thing I would like you guys to notice before I even jump into the question is when I am doing this joint distribution, note that whatever order I choose to have these joint conditional probabilities doesn't matter because the product is commutative. So I can switch up the order. So whatever order you choose to eliminate the variables doesn't matter. We will see a bit that it might give you performance benefits, but in terms of actual correctness, you can do them in any order. So let's begin by solving our first question. We are given this space net over here that's a little complicated with all these variables from t to z. And we want to find the query, the probability of y given plus z. So the ones that we want to keep are y and plus z. Everything else we want to eliminate. So t, u, v, w, x, y, we all want to get rid of. So given these conditional probability, given the space net, we know that we have these conditional probabilities. Of course, they were also given to us. But now that we have these, we can begin our elimination process. One thing I would like to note, whenever we write factors in this class, what we basically mean is that whenever we have a factor of variables a and b, or anything else, we're saying that this is proportional to the probability of a and b. Of course, in our first example that has been done for you, we see that it is plus c given t. In fact, this factor, I will go so far to claim that this is equal to the probability of plus c given t. This can be done by using Bayes' rule, but notice that this is also proportional to the probability of plus c and t by Bayes' rule as well. So we're just going to go ahead and we're going to solve this question. With the first example complete, our remaining factors are going to be this. We want to eliminate t, so we look for all the ones that contain t. That's going to be the first one, the second one, the third one, the fourth one, and our newly created factor 1. So let's make a new factor, factor 2. I'm actually not going to fill it in yet, but I'm going to first write out the right-hand side. So we're going to sum over all the possible values of t, and then we multiply out all of the ones that contain t that I just underlined previously. So that's going to be the probability of t, the probability of u given t, the probability of v given t, the probability of w given t, and the factor we just created containing plus c and t. So this is a huge factor. Let's go check which one are the variables that we would be left with if we summed out t. We would have u, we'd have v, we'd have w, and we'd have our plus z. So now we have created a new factor, and all of the old ones that contain t, we can eliminate. So now the only factors that we have left are going to be, let me just draw it out here, the probability of y given v and w, so that's that one, And we have our newly created factor, f2, which has all these variables. Okay, so now we've eliminated one variable. We have a lot more to go. So let's just go on to u. So we're going to create a new factor 3. I'm going to first leave it blank because we're not quite sure which one it is. We're going to sum over all the possible values of u, which are actually only factor 2. So factor 2, consisting of u, v, w, and plus c. So now that we have this, we can see that the ones that are not u are going to be v, w, and plus c. And we get to eliminate this factor that we get to create a new factor from this one, so we can get rid of that. Now our new factors, factors that still remain, are going to be the probability of y given v, w, so that one refuses to leave, and the third factor, our new factor that we just created, which is f3 of v, w, and plus c. Okay, so moving along, we want to now eliminate v, and then we're going to eliminate w. So let's just go ahead, do the same thing, create a factor 4. We don't know what's in there yet. Let's first sum over all the possible values of v, and the ones that contain it are both of our remaining factors. So let's just multiply them together. Times factor 3, v, w, plus c. So the ones that we have here in factor 2 is going to be w, y, and z. Okay, so let's write it out. And then these two previous factors both go away. Instead, we have this created new factor. And the only one that we have now at this point is factor 4, which is this. So moving right along, we only have one more variable to eliminate, which is w. Feature 5, let's create a factor. I'm still not going to fill it in. I'm going to have the sum over all the possible w's. And then the only one that contains w is our only remaining factor. So we just sum over all the possible w's. And the only ones remaining in our last one is going to be y and plus c. Notice that these were the only variables that we wanted in the first place. In fact, this value, as I said before, is proportional to the probability of y and plus c, which is very nice for us. So now that we have all this done, in order for us to obtain this query that we wanted to get in the first place, how would we do it? Well, you just normalize it, because we already have the joint probability. In order to get just this conditional probability by using Bayes' rule, we know that this is equal to the probability of y and z divided by the probability of z. And the probability of z is just going to be the sum over all the possible y's, which is the probability of sum over all the probabilities of y of probability of y plus c. Notice that because this value is proportional to factor, and if we hadn't included constant both in here, it's going to be the same thing because it would have crossed out anyways. So this is equal to the factor 5 of y plus c divided by the sum over all the y's of the fifth factor. And this is our final solution. So now we have solved the query. Very nice. So a bit of reflection on what we just did. What was the size of the largest factor? So remember that the factors we have here, each of these, we can think of them as a kind of like a pseudo-joint distribution. So each of them is going to have a probability table, a conditional probability table, with a number of rows corresponding to all the possible values that the free variables can take. So the size of the largest factor is going to be the one with the most free variables. So we can look back at them, and we say that that is factor 2. So that contains 1, 2, 3, 3 free variables. Notice that plus t is not a free variable, so we don't need to worry about that. So the biggest one is factor 2, containing u, v, w, and plus c, with 3 free variables. 3 free variables. So then the size of the final thing is going to be, each of them can take 2 values, because they are booleans. It's going to have 8 rows. So it's quite large. Not ideal. We can possibly do better, which is what the next question asks. So is there a better elimination order? And the answer is actually yes. Because remember that elimination order actually does not matter, that we're going to get the correct answer regardless. Notice that a general heuristic, let me scroll back up so we can see the BaseNet, is the reason why we had this giant feature 2 in the first place is because we eliminated a variable t too early on when there were too many things, and we ended up having to join a lot of possible conditional values. So what can we do instead? We can instead eliminate them in a slightly smarter order. That way we don't have to deal with this giant situation. So we can first eliminate x, and then we can eliminate u, and then we can finally eliminate t, and then v, w. And then that would give us a smaller factor. In fact, let me just write that down. X, u, t, v, and w. So if we eliminate in this order, we see that each time we eliminate, this one is only going to have 1 free variable. When we eliminate u, this one only has 1 free variable. When we eliminate t, we're only going to have 2 free variables. Same for when we eliminate v and w. And then ultimately, this is going to be very nice because we will never have a factor that has more than 2 free variables, which means the largest one is only ever going to be, not 2 to the 4, 2 squared, which is only going to be 4 rows long, which is much better than 8, obviously for memory-wise. Okay, so now we're going to talk about BaseNet's representation and independence. So question 2 of the worksheet. So the first part asks us to find the joint probability distribution from this BaseNet, which is fine. So looking at it, this is very much a very mechanical process. We look at all the edges and all the variables and see how they relate to each other. So we see that A does not depend on anything, C depends on A, B depends on A, etc. So let's just write out the joint probability distribution as a product of all these relationships. So let's start from upper left to bottom right. So let's have the joint distribution is equal to the probability of A times the probability of B given A times the probability of C given A times the probability of D given B, which is this one, times the probability of E, which doesn't depend on anything, times the probability of F given D and E, because we see that there are 2 edges into it. And then the last one is the probability of G, which is not standalone, the probability of G, which depends on D. Let's see if I'm missing anything. Okay, nope, that's it. We got everything. So this is going to be our joint distribution. Now let's look at some other properties of the BaseNet. It asks us, for each of the nodes, how many entries do the, actually let me rewrite this, let me call this the conditional probability tables. For each of these variables have, well, we can quickly just see the one for A, this is just going to be A, it doesn't depend on anything. So this is going to be probability of A. The only free variables of here are A. If there are 4 values, it's 4 to the first power, which is equal to 4. Perfect, easy. Well, then let's go to D. What does D depend on? D depends on B. We only have to deal with what D depends on. So we get that D depends on B. So if we wanted to find the value of D, we would only have 2 free variables to deal with. So it's 4 to the second power. going to be 16. And then the last one it wants is f. So for f, we have probability of f given d and e. So there's 1, 2, 3, 4 variables for cubed. I don't actually want to calculate that, so we're just going to leave it like that. Okay, so now we're going to have some more fun with the idea of independence in base nets. Let me begin by introducing a concept of triples, which are independent triples or dependent triples. So let's take a look. If we have two parents that both have a common child, if none of them are observed, we know that the parent is independent from the other parent, because clearly they don't affect each other. And the child is dependent on both of the parents. However, if we have the situation where the child is observed, all of a sudden, now that if we know something about the child, knowing something about one parent is going to give us something about the other parent. So this means that all of a sudden, knowing the child makes the parents not conditionally independent from each other. So they are independent from each other in this situation, but they are not conditionally independent from each other given the child. Well, that's the first one. Let's explore a second idea. What if we reverse it? We have a single parent and two children. So, are these two children independent from each other? Well, clearly we can see that they are not, because they both have something to do with that parent. That parent is going to affect both of them. So they are not independent. But what about conditionally independent given the parent? So what happens if all of a sudden we observe this parent? Then, actually let me reverse it that way. So this is, they are independent. But what if instead I observe the parent? Then if we know what the parent is already, then this child is not going to give us any additional information about this child if we already know something about the parent. So in this situation, it is not independent, but it is conditionally independent given the parents. So these are all the situations where they are independent of some form, both conditionally and directly, and this is some form of dependent. I'm going to keep them in quotes because they're not strictly like that. One more thing I'm going to have is I'm going to have this last idea, which is three of them in a row. So let's have them be like this. So now we're going to look at the two outer ones. So are the two outer ones independent or dependent? Well, clearly we know that they are dependent of each other. Knowing one is going to tell us what the other one is like downstream, and similarly upstream. So obviously they are not independent of each other. But what if instead I tell you I observe the middle one? Then all of a sudden, knowing one will not tell us any more information about the other one if we already know something about the middle node. So in this situation, we have something that's very similar to the common parent, which is they are dependent of each other, but they are conditionally independent given the middle node. Okay, now that we have these, we have the building blocks to do part 3. So let's take a look at all of them. So we have B. Is B independent from C? Let's take a look. Here is B, here is C. Now that we have these 2 points, we see that they have a common parent A. So this is very similar to this situation here. So they are not independent from each other. Let's cross it out. Well, what about A and F? We have A over here, and we have all the way downstream over here, F. So this is very similar to our first situation. Oh, let me draw it back out here. That is very similar to our first situation over here, which they are conditionally independent given the middle node, but they themselves are not independent. So this is not independent. What about D independent from E given F? So let's find where they are. So D, here is D, here is E, and here is F. So this is very similar to this situation, right? We have 2 common parents, for two parents for a common child. And of course, we saw that they were not conditionally independent, so this is not correct either. But then let's look at the next one. We have E, A, given D. So let's see. Do they have any common children? So eventually, yes, they have a common children, F. But before we reach F, A is independent from F, given D, because it is conditionally independent by this situation. So even though they have a common child, because A is independent from its child, given D, we know that actually this situation, they are in fact conditionally independent, given D. So we found our first independence. Let's look at this one. So we have F independent from G, so these two, given D. Okay, well, this one's pretty simple. We have our common parent situation where we observe the parent, so they're independent from each other, conditionally independent from each other. Okay, the next one, we have B is over here, we have F is over here, and then we are given the middle one, D. Wow, that's even simpler. That is just the situation exactly. So this is conditionally independent from each other. What about C from D? We have C. C and G. We have C over here. We have G over here. Let's see. They do have a common parent A. So now we have a situation here. And this A is not observed. So that means that they are not independent from each other. Okay, last one. We have D and E. They have a common child. They have no common parents. Nothing of that form. Their only common child is F, but it's not observed. We have this situation here, which means that this final one is independent. Okay, so now we're going to start doing parts D and E. So we're going to look at what it means to be independent using conditional distribution table. So part D asks, what are all non-conditional independence assumptions? So we're not talking about like A independent from B given something anymore. We just want what happens between each variable. So let's look at all of them. So clearly we can see that. So let's start with what is not independent. What is not independent? So let's start with A and B. Are they independent or not? So we can look at the conditional probability table. And remember that independence means that knowing one will not give you more information about the other. So we look at the table, we see that if we know the value of A, we definitely know something about the probability of B. Because we see that 0.9 versus 0.1 and 0.6 versus 0.4. So we know that in this situation, A is not independent from B. So we write it like that. What about between B and C? Let's take a look at this one. B and C. If we know something about B, do we know something about C? Looking at this conditional probability table here, we see that if we know B, either it is plus B or minus B, it doesn't actually change the conditional probability table. So that doesn't give us any additional information. So in this situation, even though we saw this conditional probability table, B is actually independent from C. Okay, well then the last conditional probability table that we see here is C and D. We can apply the same method. Does knowing C tell you anything about D? We see that the distribution is clearly not the same between these two. So knowing plus C versus knowing minus C is going to give us different probabilities. So these two are not independent. So now let's just list out all of the independent ones. So we have that A is independent from C, A is independent from D, and B independent from C, and B is independent from D. Very nice. Not super complicated. We have this set that are independent and this set that is not independent. Now, we can do part E, which asks us if we know that these are true, then which of the following Bayes nets are we able to use to represent it? So recall that if we have any extra conditional tables, even if they are actually in fact independent, we are fine. We'll just get something similar to what we had before in the relationship between B and C, because they were independent, but we still were able to have a conditional probability table between them. However, that's not true for if they are not independent. Then we must have an edge between them. So in these situations, we just look at these 6 Bayes nets, and then we want to see, of these 6, which ones necessarily are able to represent that A is not independent from B and C is not independent from D. So right off the bat, we are able to look and we can be like, okay, so this one is fine because we literally see the arrows between A and B and C and D. This one's also fine for the same reason. This one's also fine because this is probably exactly what we want. But of course, it doesn't matter. Let's not have any biases there. Now the question between these 3, are they okay? So clearly we see here this is not okay because this is saying that C is independent from D, which we don't want. Similarly here, we don't want this one because they say that A is independent from D in this situation. At first glance, this upper right-hand one might seem like it would work, right? Because we see that there is some relationship between C and D, and there is some relationship between A and B because they have common parent here and then a middle node in between here. But however, recall that these independencies are actually true. So these truly exist. So that means if A is independent from C, this can become an empty edge. So technically this edge doesn't actually exist. Similarly between A and D, so this kind of becomes an empty edge as well. Similarly for this last one, we have B and C. This is also an empty edge. So this kind of ends up being A and B are not independent from each other, and C and D are not independent from each other. So this one does not work either. A little more rigorously, you can think of it as these represent that they are there's too many independencies here that are conditional, so and become easily conditional independent. So in that case, it wouldn't work, especially since there's a lot of true independencies. Okay, so now let's start with this question where we have like an actual scenario. So we want to build a advanced safety feature for this self-driving car, and we have a few things that we depend on. If the driver's eyes are open or closed, steering wheel is being touched or not, car is in the lane or not, car is speeding or not, driver's heart rate, and car's radar. So we want to use that to see if they're like sleeping or if they might crash. The first question they ask is for us to draw the Bayes net associated with it. So if we read the question, we will have some dependencies, but we don't need to worry too much because they actually just list them out for us, which is very nice of them. So they tell us that E, W, H, L, and C are all influenced by A. So let's just draw the arrows to all of them. C is influenced by these 4, which is A, which we already have that, S, L, and R. So that's going to be our Bayes net. Nice and simple. So using this Bayes net for part G, they want us to mark the independent assumptions that must be true. Okay, so this is, I will say, this is a little bit too not to be worried, because we will, in this class, we will only very slightly test you on this, but let's just go over it for sake of this example. So let's start with E independent from S. We have E, we have S. They share they don't share a common child. Oh, but that doesn't matter either way. They don't share a common parent, nor do they have a node in between them. So they are independent from each other. Nothing super special. What about W and H given A? So now this is the situation where we have a common parent, but the common cause, A, is observed. So they are indeed conditionally independent from each other. What about S and R. So we have S over here, we have R over here, they have a common child, but the common child is not observed, so they are just independent from each other. Very nice. What about E and L if we don't observe A? So E and L, knowing something about E will tell us something about L because A is not observed. It will give us additional information. So this is not independent from each other. What about L and R? We have these two, and we observe C. So now that we observe C, one item will tell us a little bit about each other if we know the value of C. So that is not independent. What about W and R? They have nothing in common. This is totally fine. This was very easy. What about A and C? Oh my god, it's directly involved. Of course it's not going to be independent. E, C, given L. It doesn't actually help us because we actually have a common parent in this situation too that is unobserved. So this is not independent as well. Now that we have some experience with BaseNet, let's go on and move on to some slightly more interesting questions. So we have this sensor that tells us that it is in the lane and the car is not speeding. And we want to calculate this probability, the probability of it crashing, given that we have these two information. So we can do this by variable elimination, and they want us to eliminate it in this order. So they want us to go like this, R. So let's just write it out. Let's start with the first one. Actually, before we do that, let's first write out what are the factors. Let's start with, let's just write it here. There's the probability of A. We see that here. There's the probability of R happening. There's also the probability of S happening, but we're not going to write it because it'll just be minus S, right? So there's that, but we don't need to include that. So let's instead just move on. We have the probability of E given A, the probability of W given A, the probability of H given A, the probability of S given plus L, A minus S, and R, and then, oh, not S, this is C, my mistake. So this is C given all this stuff. We also know the probability of plus L given A, which actually in this case, if we already observed this, we don't need it as well. But I'm just going to keep it here, just for the sake of it. So if we were to do the elimination, we start by using R. We're going to generate a factor that consists of everything with R. Let's just cross everything out so we can keep track. This one has an R. This one has an R. Nothing else has an R. So we're going to create a factor that consists of all the variables that were in that. So we have the factor 1. We have C plus L, A, and minus S. So now we have all these remaining factors. I'm just going to get rid of this because it's not super important. Now, this has two free variables, so this is going to have whatever domain size to the power of 2. We'll leave that there. We'll notice that there's two free variables. Let's make the next one. In fact, this is going to be our largest one. Why do I know that? Because now that we eliminate A, notice that every single one of them have A. So the next one that we create, we're going to remove all of everything, even the new factor that we created, and that's going to have C, E, W, H, plus L, minus S, and now we have 4 free variables, and no other variables that we can possibly ever join, so there's no way that any other factor can be bigger, so we have found our largest factor. This is pretty bad. So the next question, write down a more efficient variable elimination ordering. As long as we have anything, as long as we eliminate A, after we eliminate any of these other ones, W, E, W, or H, then we're going to get a smaller factor. So one possible ordering we can do is R, E, W, H, and then finally we eliminate A. So this is going to make it much better because we wouldn't have this big ugly thing over here. which would make it a lot faster and more efficient.